When people think about the true size of the Andromeda Galaxy, it is often imagined as something already known, already measured, already settled. Andromeda is usually described as our nearest large galactic neighbour, a spiral galaxy much like our own, sitting at a clear distance with a diameter that can be written down as a number. In many descriptions, its size is presented as a simple comparison, larger than the Milky Way, or roughly similar depending on the source. This creates an intuitive picture of Andromeda as a neatly bounded island of stars, floating in space with a shape and scale that are easy to grasp. Yet even within astronomy, the idea of how large Andromeda truly is has shifted quietly over time, not through dramatic discoveries, but through gradual refinements in how size itself is understood. At first glance, the question seems straightforward. A galaxy has stars. Those stars emit light, and that light defines an outline. Early measurements followed this logic closely, focusing on the bright spiral disk that stands out clearly against the darkness of space. Within that glowing structure, Andromeda appears orderly and contained, its spiral arms tracing a familiar pattern. But as observations accumulated, astronomers began to notice that different methods produced different answers, and that each answer depended on what was included and what was left out. The uncertainty did not come from confusion, but from the realization that galaxies do not end where brightness fades, and that the absence of light does not mean the absence of structure. The science behind this is more subtle than the common picture suggests. Instead of a sharp boundary, galaxies tend to thin out gradually, becoming more diffuse as distance from the center increases. Stars grow sparser, gas becomes harder to detect, and gravitational influence extends far beyond anything directly visible. This means that size is not a single property, but a layered concept shaped by observation, definition, and perspective. In this video, we will explore the true size of the Andromeda Galaxy slowly, step by step, allowing each layer to settle before moving on to the next. The goal is not to arrive at one final number, but to understand how astronomers think about size in systems that have no clear edge. Welcome to AstraFlow. Here, science drifts quietly, and understanding comes without effort. If you find this exploration helpful, you're gently invited to share your thoughts or follow along for future journeys. Now, let's begin. To start, it helps to rest with the idea that Andromeda is familiar not because it is simple, but because it has been observed for a very long time. It is visible to the naked eye under dark skies, appearing as a faint, elongated smudge. For centuries, it was thought to be a cloud within our own galaxy. Only in the last 100 years did it become clear that Andromeda is a galaxy in its own right, containing hundreds of billions of stars. This historical shift already hints at how easily size can be misjudged when distance and scale are involved. What once seemed small and nearby turned out to be vast and remote. When astronomers first began measuring Andromeda's size as a galaxy, they relied primarily on optical light. Telescopes collected photons from stars, mapping the bright regions where stellar density was highest. These early maps showed a disk extending roughly a couple 100,000 light-years across. This number, repeated in textbooks and documentaries, became part of the standard description. It felt solid, dependable, and precise. Yet even as this value circulated, it carried an unspoken assumption that the visible disk represented the galaxy as a whole. Over time, deeper observations began to soften that assumption. Improved detectors revealed faint stars far beyond the previously identified edges. These stars did not form a neat disk or spiral pattern. Instead, they occupied a loose, extended halo surrounding the brighter core like a quiet, diffuse envelope. This halo was not immediately obvious, and it did not announce itself with strong light. It required patience to detect and careful analysis to confirm. As it became better understood, the effective size of Andromeda quietly expanded, not because the galaxy had changed, but because human perception of it had. This gradual expansion of understanding is a recurring pattern in astronomy. As instruments improve, structures once thought complete reveal additional layers. Gas clouds extend farther than stars. Faint stellar populations trace ancient interactions. Gravity reaches beyond both. Each layer challenges the idea that a galaxy can be cleanly separated from its surroundings. Andromeda, in this sense, is not unusual. It is simply close enough and studied enough for these subtleties to be noticed in detail. Another important aspect of size is time. The Andromeda Galaxy we observe today is not fixed in form. Over billions of years, it has grown by merging with smaller galaxies and by pulling in surrounding material. Streams of stars, stretched thin by gravity, still linger as evidence of these past events. These streams extend the galaxy's influence outward, blurring the distinction between what belongs to Andromeda and what is merely passing by. When size is viewed through this temporal lens, it becomes less about present boundaries and more about ongoing processes. Even so, the human mind often prefers clarity. We like edges, borders, and numbers that can be compared. This preference shapes how questions are asked and how answers are framed. When someone asks for the true size of Andromeda, they may be expecting a single figure expressed in light years that settles the matter. Science, however, often responds with context rather than closure. The size of a galaxy depends on whether one is measuring light, mass, motion, or influence. Each approach is valid within its own framework, and each reveals a different aspect of the same object. As we move forward in this exploration, we will gradually shift from the most familiar definitions of size toward those that are less intuitive but more complete. We will begin with what can be seen directly, then extend outward into regions revealed through careful observation and indirect measurement. At each stage, the emphasis will remain on continuity rather than contrast. There will be no sharp transitions because the galaxy itself has none. Instead, the structure of Andromeda will unfold as a series of overlapping layers, each fading gently into the next. For now, it is enough to recognize that the question of Andromeda's true size is not a challenge to established knowledge, but an invitation to refine it. What appears simple at first glance becomes richer as attention deepens. This is not a correction of past understanding, but an extension of it. Andromeda remains the same galaxy it has always been. What changes is the way it is seen, measured, and quietly understood. With this perspective in place, we are ready to move closer, orienting ourselves in space and establishing where Andromeda sits in relation to us, before continuing outward into the details of its structure. To understand the true size of the Andromeda Galaxy, it helps first to be clear about where it is. Location provides a kind of calm foundation. Without orientation, size becomes abstract too quickly, and the mind has nothing steady to rest on. Andromeda is not scattered somewhere randomly across the universe. It occupies a specific position in the sky, one that has been known and quietly observed for centuries. From Earth, it lies in the constellation Andromeda, appearing as a faint, elongated patch of light when conditions are dark and clear. This simple fact already places it in a different category from most galaxies, which require instruments to be seen at all. In terms of distance, Andromeda is close by cosmic standards. Light from the galaxy takes a little over 2 million years to reach us. This number can be stated precisely, but its importance is not in precision. What matters is that this distance is small enough for detailed study, yet large enough that the galaxy is seen as a whole rather than from within. We observe Andromeda from the outside with a clear view of its overall structure, something we cannot easily do with the Milky Way because we are embedded inside it. This external perspective makes Andromeda a reference point, a kind of nearby example through which astronomers learn how large spiral galaxies tend to be. The position of Andromeda relative to the Milky Way is also stable and well measured. Both galaxies are members of a small collection known as the Local Group, bound together by gravity. Within this group, Andromeda and the Milky Way are the two dominant members, each influencing the motion of smaller satellite galaxies around them. The distance between the two is large enough that they remain distinct systems for now, but close enough that their outer regions are already beginning to feel each other's presence. This relationship will become more important later, when size is considered not just as a physical extent, but as a region of influence. From our vantage point, Andromeda appears tilted. We do not see its spiral disk face on, but at an angle. This orientation affects how its size is perceived in images. One side of the disk appears compressed, the other stretched, and dust lanes cut across the light unevenly. Astronomers account for this tilt when measuring dimensions, correcting for perspective to estimate the galaxy's true shape. These corrections are routine and precise, yet they serve as a reminder that even basic measurements depend on the interpretation. What is seen is not always what is measured. When distance and orientation are combined, a clearer picture begins to form. Andromeda's bright disk spans several degrees across the sky, making it appear surprisingly large compared to most celestial objects. This apparent size, however, can be misleading. Objects closer to us naturally appear larger, even if their physical size is modest. In Andromeda's case, both its actual size and its proximity contribute to its prominence. This dual effect has helped establish its reputation as a large galaxy, even before its full structure was understood. The process of locating Andromeda is therefore not just about coordinates or distance values. It is about anchoring perception. Knowing where the galaxy is, how far away it lies, and how it is oriented allows later discussions of size to remain grounded. Without this anchor, measurements risk floating free of context, becoming numbers without meaning. By starting here, the idea of size stays connected to space, position, and relationship. As astronomers refined Andromeda's location and distance over the 20th century, estimates of its size became more reliable. Improved distance measurements meant that angular dimensions on the sky could be translated into physical lengths with greater confidence. This reduced uncertainty, but it did not eliminate complexity. Even with distance well known, the question remained: which parts of the galaxy should be included? The bright disk was easy. Everything beyond it required additional thought. What remains steady is that Andromeda occupies a clear place in our cosmic neighbourhood. It is not an abstract example drawn from a distant survey. It is a nearby system, moving slowly toward us, sharing the same local gravitational environment. This proximity allows astronomers to study faint features that would be invisible in more distant galaxies. As a result, Andromeda often appears larger in scientific descriptions than galaxies observed only through their brightest regions. This is not because it is uniquely extended, but because it is close enough for its subtle outskirts to be seen. As this orientation settles, the next step is to look more closely at what we mean when we speak of a galaxy's size at all. Distance and location provide the frame, but definition provides the content. From here, the idea of size will begin to separate into distinct components, each revealing a different aspect of Andromeda's true extent. Once Andromeda's position is clear, the idea of size can be approached more carefully. In everyday language, size usually refers to a single dimension: how wide something is, how tall it is, how far it extends from one side to the other. This way of thinking works well for solid objects with clear boundaries. Galaxies, however, are not solid, and they do not have edges in the usual sense. When astronomers speak about the size of a galaxy, they are choosing a definition that depends on what aspect of the galaxy they are describing. This choice is not arbitrary, but it is specific, and understanding it helps the question feel less uncertain and more precise. One common definition of size focuses on starlight. In this approach, a galaxy extends as far as its stars can be detected above the background of space. This seems natural, because stars are what make galaxies visible in the first place. Using this method, astronomers measure how the brightness of the galaxy changes with distance from its centre. Where the light becomes indistinguishable from the background, an effective boundary can be drawn. This boundary is not sharp, but it provides a practical way to describe the extent of the luminous structure. For Andromeda, this luminous disk is large and well studied, and for many years it served as the primary reference for the galaxy's size. Another way to define size considers gas instead of stars. Galaxies are not made only of stars. They also contain large amounts of gas, especially hydrogen, which does not shine brightly in visible light, but can be detected through radio observations. This gas often extends far beyond the region where stars are concentrated. When size is defined in terms of gas, galaxies become noticeably larger. In Andromeda's case, the hydrogen disk stretches well beyond the bright spiral arms, forming a faint extended structure that would be invisible without specialized instruments. This does not contradict the stellar definition of size, it simply describes a different component. There is also the concept of size defined by gravity. Every galaxy has a region where its gravitational pull dominates over the influence of neighbouring systems. Within this region, stars, gas, and smaller galaxies tend to move in response to the galaxy's mass. This gravitational boundary is not marked by light or matter density, but by motion. It is inferred from how objects move rather than from how they appear. When size is defined in this way, galaxies become larger still, often extending far beyond anything directly observable. For Andromeda, this gravitational region includes not only its main body, but also a system of satellite galaxies and diffuse material bound to it. These different definitions are not competing answers to the same question. Instead, they are layers of description, each appropriate to a different scientific purpose. If the goal is to compare the visible appearance of galaxies, the stellar disk is the most relevant measure. If the goal is to understand star formation, the gas distribution becomes more important. If the goal is to study cosmic structure and dynamics, gravitational extent takes precedence. Each definition reveals a different aspect of what it means for Andromeda to be large. What makes this approach feel unfamiliar is that the word size is often used without specifying which definition is being applied. In casual conversation, this ambiguity is usually harmless. In astronomy, it can lead to confusion if not made explicit. One source may state that Andromeda is about 200,000 light-years across, while another may describe it as extending nearly 1 million light-years when its halo and gravitational influence are included. Both statements can be correct within their respective frameworks. The difference lies not in disagreement, but in scope. It is also important to note that these definitions overlap rather than replace one another. The luminous disk sits within the gas disk, which in turn sits within the stellar halo, all of which are embedded in a much larger dark matter halo. There are no clear boundaries between these components. Instead, each fades gradually into the next. This gradual transition is why astronomers often speak in terms of characteristic sizes rather than absolute limits. A characteristic size describes where one component becomes less dominant, not where it abruptly ends. For Andromeda, this layered structure is particularly well documented because of its proximity. Faint stars that would be impossible to detect in distant galaxies can be resolved and studied. Subtle motions can be measured with precision. As a result, Andromeda often appears larger and more complex in scientific descriptions than more distant galaxies of similar type. This is not because it is fundamentally different, but because it is close enough for its full structure to be revealed. As this way of thinking settles in, the question of Andromeda's true size begins to feel less like a search for a single number and more like an exploration of structure. Size becomes a description of extent, influence, and composition rather than a fixed measurement. This shift does not make the concept vague. Instead, it makes it richer and more accurate, reflecting the nature of galaxies themselves. With this understanding of what size can mean, the next step is to begin with the most familiar layer, the visible stars that form Andromeda's bright disk. From there, the exploration can move outward, one component at a time, allowing the galaxy's full extent to emerge gradually. When discussions of the Andromeda Galaxy begin with its stars, they usually focus on what can be seen most clearly: the luminous disk made up of hundreds of billions of suns. This stellar disk is the region that first drew attention when Andromeda was recognized as a galaxy beyond the Milky Way. It is bright, structured, and comparatively easy to map. Spiral arms curve outward from a dense central bulge, and along these arms stars cluster more tightly, tracing patterns shaped by rotation and gravity. For many years, this visible arrangement defined Andromeda almost completely in the public imagination. The size of this stellar disk can be described by how far the majority of its stars extend from the centre. Astronomers measure this by counting stars and measuring their brightness at increasing distances outward. As one moves away from the core, the density of stars decreases steadily. There is no point where stars suddenly disappear. Instead, the disk grows thinner, its light more diffuse, until it blends into the background. To work with this gradual change, astronomers choose a threshold, a level of brightness or density below which the disk is considered to have effectively ended. This threshold is practical rather than absolute, but it allows consistent comparisons between galaxies. Using this approach, Andromeda's stellar disk is found to be exceptionally large. Its diameter is often quoted as being on the order of 200,000 light-years, making it somewhat larger than the Milky Way's visible disk by many estimates. This comparison, while common, should be held gently. Measurements of our own galaxy are more uncertain because we observe it from within. In contrast, Andromeda is seen from the outside, allowing its structure to be traced more cleanly. The apparent size difference may reflect this observational advantage as much as any intrinsic disparity. Within the disk, stars of many ages coexist. Younger, hotter stars tend to trace the spiral arms, glowing more brightly and standing out against the darker regions between them. Older stars are distributed more evenly, forming a smoother background of light. This mix contributes to how the disk's edge is perceived. Regions dominated by younger stars fade more quickly, while older populations extend farther out, maintaining a faint but measurable presence. As a result, the exact boundary of the disk depends partly on which stars are being emphasized. Counting visible stars also involves careful correction for dust. Andromeda contains lanes of interstellar dust that absorb and scatter light, making some regions appear dimmer than they truly are. Astronomers account for this by observing at multiple wavelengths, including infrared light, which passes through dust more easily. These observations often reveal stars hidden from optical view, subtly extending the perceived size of the disk. Each refinement adds detail rather than drama, adjusting the picture without overturning it. What remains consistent is that the stellar disk, while impressive, represents only a portion of Andromeda's full extent. It is the most immediately recognizable component, and for many purposes it serves as a useful reference. Yet even here, the idea of size is already shaped by choices about thresholds, wavelengths, and stellar populations. The disk's boundary is not a wall, but a zone where stars become increasingly sparse. As attention rests on this luminous structure, it becomes clear why early measurements focused here. The disk is where most of the light is, where structure is most apparent, and where comparison with other spiral galaxies feels most intuitive. It provides a stable starting point, a layer of Andromeda that can be described with relative confidence. From this foundation, the exploration can move outward, into regions where light fades and other forms of evidence take over. Allowing this image of the stellar disk to settle, the next step is to examine what happens at its edges, where brightness thins and the notion of a clear boundary begins to dissolve. As the bright stellar disk of Andromeda thins toward its outskirts, the idea of an edge becomes less certain. There is no line that can be drawn with confidence. No sudden drop where stars simply stop. Instead, the disk fades gradually, its structure becoming quieter and more diffuse. Astronomers describe this region not as a boundary, but as a transition. The familiar spiral pattern loosens, star density falls, and light becomes increasingly difficult to separate from the darkness of intergalactic space. This fading is not uniform. In some directions, stars extend farther than expected, while in others the disk appears to end sooner. These irregularities are not errors, but clues. They reflect the galaxy's history of rotation, interaction, and gradual growth. Over billions of years, gravitational forces have pulled stars into elongated paths, thickened the disk, and stirred its outer regions. What remains is a structure that looks smooth from a distance, but reveals complexity when examined closely. To describe this fading edge, astronomers often use statistical tools. Instead of asking where the last star is, they ask how the average density of stars changes with distance. This produces a curve rather than a cutoff. The curve declines steadily, indicating that stars are still present even where the disk appears to have ended. The choice of where to say the disk stops is therefore a matter of convention, guided by practicality rather than by a physical boundary in the galaxy itself. This approach can feel unsatisfying at first, especially if one expects size to be something definite, yet it reflects the nature of galaxies as dynamic systems. Stars do not respect boundaries. Their orbits can carry them far from the dense regions where they formed. Over time, this mixing smooths out sharp features and creates extended low-density outskirts. The fading edge of Andromeda's disk is a natural outcome of this process, not an anomaly. Observational limits also play a role. Even with powerful telescopes, there is a point at which faint stars blend into background noise. This does not mean the stars are no longer there, only that they are harder to detect. As instruments improve, the detectable edge moves outward. This has happened repeatedly in the study of Andromeda. Each new survey has revealed stars at greater distances, gently expanding the perceived size of the disk without changing its underlying nature. The concept of a fading edge is important because it prepares the ground for what comes next. Beyond the disk lies a population of stars that does not belong to the spiral structure at all. These stars form a halo, a roughly spherical distribution that surrounds the galaxy. The transition from disk to halo is subtle, marked not by disappearance, but by a change in the way stars are arranged and move. Recognizing this shift requires letting go of the idea that size must be tied to brightness alone. For now, it is enough to rest with the image of Andromeda's disk dissolving gently into its surroundings. The light thins, structure softens, and certainty gives way to gradual change. This is not an ending, but an opening, leading outward into regions that are quieter, older, and more diffuse, yet no less a part of the galaxy. Beyond the fading edge of Andromeda's bright disk lies a region that is easy to overlook because it does not announce itself with strong light or clear structure. This is the stellar halo, a vast, diffuse population of stars that surrounds the galaxy in all directions. These stars are not arranged in spiral arms, and they do not follow the orderly rotation of the disk. Instead, they form a loose, roughly spherical distribution, extending far into space with very low density. The halo does not replace the disk, it envelops it, adding a quiet outer layer to the galaxy's form. The stars in this halo tend to be old. Many formed early in the galaxy's history, when conditions were different from those in the disk today. Others originated in smaller galaxies that were gradually pulled in and absorbed by Andromeda over billions of years. As these smaller systems were disrupted, their stars were scattered into wide orbits, contributing to the halo's extended shape. This process leaves behind a population that is faint, spread out, and difficult to detect, yet significant in scale. Detecting the halo requires patience and precision. Individual stars are counted one by one, often using long exposures and careful filtering to separate them from foreground stars in the Milky Way. In Andromeda's case, its relative proximity makes this possible. Astronomers can resolve individual halo stars and map their distribution over large areas of the sky. These maps reveal that the halo extends far beyond the visible disk, sometimes to distances several times greater than the disk's radius. Unlike the disk, the halo does not have a clear orientation or flatness. It is thicker, more isotropic, and less influenced by ongoing star formation. This difference in structure reflects a difference in history. The disk is shaped by rotation and the steady formation of new stars from gas. The halo preserves a record of past interactions, mergers, and early assembly. In this sense, the halo is both an extension of Andromeda's size and a memory of its growth. When size is defined to include the stellar halo, Andromeda becomes much larger than its bright appearance suggests. The galaxy's effective radius increases dramatically, not because the halo contains larger numbers of stars, but because those stars are spread over such a vast volume. This is a subtle expansion of size. The halo does not dominate the galaxy visually, but it dominates the space the galaxy occupies. There is also no sharp boundary to the halo. Its density decreases gradually with distance, becoming harder and harder to distinguish from the surrounding intergalactic environment. At some point, the stars are so sparse that their association with Andromeda can only be inferred statistically through their motions and chemical signatures. This again reinforces the idea that galactic size is defined by transitions rather than edges. Allowing the presence of the halo to settle changes how Andromeda is imagined. The galaxy is no longer just a flat spiral disk with a bright centre. It becomes a layered system, with a luminous core embedded in a much larger, quieter structure. This structure extends Andromeda's reach far beyond what the eye alone would suggest. From here, the exploration can continue outward, by looking more closely at specific features within the halo itself, particularly the streams and remnants left behind by past interactions. These features stretch Andromeda's size even further, tracing paths through space that mark where other galaxies once were. Within Andromeda's stellar halo, the distribution of stars is not entirely smooth. Careful observation reveals long, faint structures stretching outward like threads, tracing paths through space that do not align with the orderly rotation of the disk. These are stellar streams, formed from the remains of smaller galaxies that once orbited Andromeda and were gradually pulled apart by its gravity. They are subtle features, visible only through detailed surveys, yet they play an important role in shaping how large the galaxy is considered to be. Each stream is the result of a slow process. As a smaller galaxy moves around Andromeda, gravitational forces stretch it, stripping stars from its outer regions. Over time, these stars spread out along the original orbit, forming elongated ribbons that can extend for hundreds of thousands of light years. The process is gentle and prolonged, unfolding over billions of years rather than through sudden disruption. What remains is not a distinct companion, but a faint record of interaction, preserved in the positions and motions of stars. In Andromeda, several such streams have been identified. Some loop around the galaxy, others plunge through the halo at steep angles. Together they reveal a complex history of growth through accretion. Each stream marks a region of space where Andromeda's influence has reached, capturing and reshaping material that was once separate. When these features are included, the effective size of the galaxy extends well beyond both the disk and the smooth halo. From a scientific perspective, streams are valuable because they provide clear evidence of past mergers. Their shapes and orientations allow astronomers to reconstruct the orbits of the galaxies that created them, offering insight into how Andromeda assembled its mass. From the perspective of size, they show that the galaxy's structure is not confined to a simple, symmetric form. It includes irregular, extended components that stretch far into space. These remnants also blur the distinction between what belongs to Andromeda and what does not, A star in a stream may be hundreds of thousands of light years from the galaxy's centre, yet still gravitationally bound. Its presence challenges any attempt to draw a clean boundary. If size is defined by what is bound, then these distant stars must be included. If it is defined by smooth structure, they may be treated as exceptions. Again, the answer depends on definition. Over time, stellar streams do not remain distinct. Gravitational interactions and orbital mixing gradually disperse them, smoothing their stars into the broader halo. In this sense, streams represent a temporary phase, a moment in the long evolution of the galaxy. Their current visibility is a result of Andromeda's ongoing growth, captured at a particular point in cosmic time. Including them in discussions of size is a way of acknowledging that galaxies are not static objects, but evolving systems with extended histories. As attention moves outward along these streams, the scale of Andromeda continues to expand. The galaxy becomes less a single object and more a region of space shaped by gravity over time. This shift does not make the concept of size less meaningful. Instead, it ties size to process, showing how the galaxy's extent is the outcome of interactions rather than a fixed property. With the stellar components now extending far beyond the visible disk, the next layer to consider is not made of stars at all. Surrounding Andromeda is a vast reservoir of gas, invisible to the eye, yet essential to understanding how large the galaxy truly is. Beyond the stars of Andromeda, there is another component that extends quietly outward, shaping the galaxy's size in a way that is not immediately visible. This component is gas, primarily hydrogen, spread thinly across vast regions of space. Unlike stars, this gas does not glow brightly in visible light. For a long time, it remained largely unnoticed, simply because the tools needed to detect it did not yet exist. Once radio astronomy developed, this hidden structure began to emerge, revealing that Andromeda occupies far more space than its starlight alone would suggest. Hydrogen gas emits radiation at a specific radio wavelength, allowing astronomers to map its distribution even when it is cold and diffuse. When Andromeda is observed in this way, a broad extended gas disk becomes apparent, stretching well beyond the luminous stellar disk. This gas forms a flattened structure, aligned roughly with the galaxy's rotation, but extending much farther out than the region where stars are densely concentrated. In some directions, it reaches distances comparable to the size of the stellar halo, overlapping with regions populated by old, faint stars. The presence of this extended gas has important implications for how size is understood. Gas responds to gravity, rotates with the galaxy, and participates in its long-term evolution. Even where star formation has not occurred for billions of years, the gas remains part of the system, bound and influenced by Andromeda's mass. If size is defined by the material actively participating in the galaxy's dynamics, then this gas must be included. The gas distribution is not perfectly smooth. It shows warps, bends, and asymmetries, especially in the outer regions. These features reflect past interactions, both with smaller galaxies and with the surrounding intergalactic medium. Over time, gravitational forces and subtle pressure effects have shaped the gas into a structure that is stable on large scales, but still responsive to its environment. These irregularities add further nuance to the idea of a clean outer boundary. Another quiet detail is that the gas does not stop abruptly. Like the stars, it becomes thinner with distance, fading gradually into the surrounding space. At the outermost reaches, the density drops so low that detection becomes challenging. As observational techniques improve, faint gas is often found at greater distances than previously known. Each improvement gently pushes the effective size of Andromeda outward, not because the galaxy has changed, but because its more delicate components are now visible. This extended gas also serves as a bridge between the inner galaxy and the larger cosmic environment. It interacts with inflowing material from intergalactic space, and with outflows driven by stellar activity in the disk. Through these processes, Andromeda exchanges matter with its surroundings, reinforcing the idea that a galaxy is not an isolated island, but part of a continuous medium. Letting this layer of gas settle into the picture further softens the idea of Andromeda as a sharply bounded object. The galaxy becomes a combination of stars and gas, both extending far beyond the bright spiral arms that dominate photographs. Size, in this context, is not just about where light ends, but about where the galaxy's material presence gradually thins into the wider universe. Beyond even this gaseous extent lies another deeper layer, one that does not emit light at all, but exerts a powerful influence on everything within it. To understand the larger scale of Andromeda's size, attention must now turn to the invisible mass that shapes its motions. Beyond the stars and gas of Andromeda lies a component that cannot be seen directly, yet dominates the galaxy's structure on the larger scales. This component is dark matter. It does not emit or absorb light in any detectable way, but its presence is inferred through its gravitational effects. When astronomers study how stars and gas move within Andromeda, they find that the visible matter alone cannot account for the observed motions. Something more extended and more massive must be shaping the galaxy's behaviour. The evidence comes from rotation. In the inner regions of Andromeda, stars orbit the centre at speeds that can be explained by the mass of the stars and gas there. Farther out, however, those speeds remain high, even where visible matter becomes sparse. If gravity were coming only from the luminous components, orbital speeds would decline with distance. Instead, they stay relatively steady. This flat rotation pattern indicates the presence of a large, unseen mass surrounding the galaxy, extending far beyond the visible disk. This unseen mass is described as a dark matter halo. Unlike the stellar halo, it is not made of stars and does not trace past mergers through visible streams. It is smoother, more extended, and far more massive than all the stars and gas combined. The dark matter halo envelops Andromeda completely, providing the gravitational framework within which the visible galaxy exists. In terms of size, this halo defines the largest scale at which Andromeda can be meaningfully said to exist as a single system. Estimating the extent of the dark matter halo involves measuring motion at great distances from the galaxy's centre. Astronomers observe the velocities of distant stars, gas clouds, and satellite galaxies, using their motions to infer how much mass lies within their orbits. These measurements suggest that Andromeda's dark matter halo extends hundreds of thousands and possibly over 1 million light-years from the centre. The exact boundary is uncertain, not because the data are poor, but because the halo fades gradually rather than ending sharply. This gradual fading is a recurring theme. The density of dark matter decreases with distance, becoming lower and lower as one moves outward. At some point, the influence of Andromeda's halo blends into the broader dark matter structure of the local group. There is no clear line where Andromeda's dark matter stops and the surrounding environment begins. Instead, there is a region of overlap, where gravitational influence is shared and boundaries are defined statistically rather than physically. Including dark matter in the concept of size transforms Andromeda from a large galaxy into a truly vast system. The bright spiral disk becomes a small, luminous core within an enormous, invisible structure. This does not diminish the importance of the visible galaxy. Rather, it places it in context, showing how much of Andromeda's presence is carried by something that does not announce itself through light. This perspective also helps explain why size estimates can differ so widely. A description focused on stars alone will produce a much smaller figure than one that accounts for dark matter. Both are correct within their intended scope. The difference lies in whether size is defined by appearance or by gravitational reach. As this invisible layer settles into the picture, Andromeda's true scale begins to feel less like a number and more like a region of influence. The galaxy is no longer just a collection of stars and gas, but a massive gravitational structure shaping the motion of everything around it. From here, attention can turn to how this influence is measured in practice, and how motion itself becomes a tool for defining size. When size is defined through gravity rather than light, motion becomes the primary guide. Astronomers do not see dark matter directly, but they observe how objects move under its influence. In Andromeda, this approach has been especially productive because many different tracers are available, each occupying a different region of the galaxy. Stars within the disk, gas clouds farther out, and satellite galaxies at great distances all respond to the same underlying gravitational structure. By studying their motions together, a coherent picture of Andromeda's mass and extent emerges. In the inner regions, rotation curves provide the first clues. As stars orbit the galactic centre, their speeds can be measured through shifts in their light. These measurements show how mass is distributed with distance. In Andromeda, as in most spiral galaxies, the rotation speed rises near the centre and then remains relatively constant far beyond the region where most stars are found. This persistence of motion indicates that mass continues outward, even where light does not. Each data point extends the inferred size of the galaxy a little farther. Beyond the disk, individual stars in the halo offer another way to trace motion. These stars move in more varied orbits, not confined to a flat plane. By measuring their velocities and directions, astronomers can estimate how strongly Andromeda's gravity still holds them. Stars that remain bound at large distances indicate that the galaxy's influence reaches far beyond the bright regions. Each confirmed bound star becomes a quiet marker of size, placed not by light, but by motion. Even farther out, small satellite galaxies play an important role. Andromeda is surrounded by dozens of smaller companions, each moving through space under its gravitational pull. By tracking their velocities and trajectories, astronomers can infer the total mass enclosed within their orbits. If a satellite remains bound while moving at a certain speed and distance, the mass of the galaxy must be sufficient to hold it. These satellites act like distant test particles, outlining the outer limits of Andromeda's gravitational domain. This method does not produce a sharp boundary. Instead, it reveals a region where motion transitions from being dominated by Andromeda to being influenced by the broader environment of the local group. In this transitional zone, orbits become less predictable, and the concept of belonging becomes statistical rather than absolute. Some objects may be loosely bound, others temporarily passing through. Size in this context becomes a probability rather than a line. What makes this approach especially calm is that it relies on consistency rather than extremes. No single fast-moving star or distant satellite defines the galaxy's size on its own. Instead, many measurements, taken together, outline a gradual decline in influence. The resulting picture is stable, even if individual details are refined over time. As more motions are measured, the outline becomes clearer, but its fundamental shape remains the same. Thinking of size in terms of motion also shifts attention away from appearance. The brightest parts of Andromeda become less central to the definition, while faint and invisible components take on greater importance. This does not diminish the value of what is seen. It simply places it within a larger framework where light is one indicator among many. As this understanding settles, Andromeda appears less like an object with edges and more like a system with reach. Its size is expressed through how far its gravity organizes motion, drawing stars, gas, and smaller galaxies into a shared pattern. From here, it becomes natural to consider how far that pattern extends, and how the galaxy's influence defines a region of space larger than its visible form. When the motions of stars and satellites are taken together, a broader picture begins to emerge, one that is less about structure and more about influence. A galaxy like Andromeda's does not simply occupy space, it organizes it. Within a certain region, matter tends to move in ways that reflect the galaxy's mass and history. This region is sometimes described as a sphere of influence, not because it has a precise boundary, but because within it, Andromeda's gravity is the dominant shaping force. This sphere extends well beyond the bright disk and even beyond the smooth stellar halo. It includes regions where stars are sparse, gas is thin, and light is almost absent, yet motion remains coordinated. Objects within this zone tend to orbit, fall inward, or move along paths that reflect Andromeda's gravitational pull rather than that of any neighbouring system. In practical terms, this means that Andromeda's size can be thought of as the volume of space where its gravity matters most. One way to describe this region is by considering escape. If an object is within Andromeda's sphere of influence, it would require a certain amount of energy to escape the galaxy's gravity entirely. Beyond that region, escape becomes easier, and motion is more strongly shaped by the combined gravity of the local group. The distance at which this transition occurs is not fixed. It depends on mass estimates, relative motions, and the distribution of surrounding matter. Still, it provides a useful way to think about size as a gradual shift rather than a sudden end. In Andromeda's case, this sphere of influence is vast. Satellite galaxies orbit at distances of hundreds of thousands of light years, and their motion suggests that they remain bound over long periods. Some satellites move on elongated orbits that carry them far out before bringing them back in, spending much of their time in regions where the galaxy's presence is felt more subtly. Including these orbits in the definition of size further extends Andromeda's effective reach. There is also a quiet overlap between Andromeda's sphere of influence and that of the Milky Way. The two galaxies are moving toward each other, and their outer dark matter halos likely already intersect. In this overlapping region, gravitational influence is shared. Objects there may be tugged gently by both systems, their motions reflecting a balance rather than allegiance to one galaxy alone. This overlap does not mean the galaxies have merged, but it does soften the idea that each occupies a completely separate volume of space. Considering size in this way makes it clear that galaxies are not isolated islands. They exist within a web of gravitational relationships, where boundaries are negotiated rather than fixed. Andromeda's sphere of influence is shaped not only by its own mass, but by the presence of neighbours and the broader structure of the local group. Its size, therefore, is relational. It depends on context as much as on internal composition. This perspective does not complicate the question unnecessarily. Instead, it aligns size with physical effect. A galaxy is as large as the region it can meaningfully shape over time. For Andromeda, that region is immense, extending far beyond anything that can be seen directly. Yet, it remains coherent, defined by slow, predictable motion rather than by abrupt change. As this idea settles, attention can begin to shift toward comparison. Understanding Andromeda's size in terms of influence naturally leads to asking how it compares with the Milky Way, and how two such large systems coexist within the same local environment. When Andromeda is compared with the Milky Way, the question of size becomes more grounded, less abstract. Both galaxies are large spiral systems, formed through similar processes and shaped by comparable physical laws. Because we observe Andromeda from the outside and the Milky Way from within, the comparison is never perfectly symmetrical. Still, placing them side by side helps clarify what is typical, what is uncertain, and what truly distinguishes one from the other. In terms of visible structure, Andromeda's stellar disk appears larger than that of the Milky Way by many estimates. Its spiral arms extend farther, and its overall luminosity suggests a slightly higher stellar mass. These differences, however, are measured with more confidence for Andromeda than for our own galaxy. From inside the Milky Way, dust obscures large regions, and distance estimates are more uncertain. As a result, the apparent size difference may partly reflect perspective rather than intrinsic scale. When gas is included, the comparison becomes more balanced. Both galaxies possess extended hydrogen disks that reach well beyond their bright stellar regions. The exact extent of these gas components is still being refined, but they appear broadly similar in scale. Each galaxy's gas responds to gravity in comparable ways, forming warped, extended structures that blur the transition between galaxy and environment. In this layer, Andromeda is not dramatically larger, but comfortably comparable. The dark matter halos of the two galaxies are even closer in estimated size. Measurements of satellite motions and orbital dynamics suggest that both halos extend hundreds of thousands of light years and contain masses on the order of 1 trillion times that of the Sun. There is uncertainty in these estimates, but the uncertainties overlap. Rather than one galaxy clearly dominating the other, they appear to be matched systems, each exerting a similar gravitational presence within the local group. This near parity has consequences. Because the Milky Way and Andromeda are similar in mass and size, their interaction is mutual rather than one-sided. As they move toward each other, neither acts as a small object falling into a much larger one. Instead, they are two extended systems whose outer regions are already beginning to overlap. This overlap does not require dramatic change. It unfolds slowly through subtle shifts in motion and shared gravitational influence. Thinking about size through comparison also highlights a quiet truth. There is nothing singular about Andromeda's scale. It is not exceptionally large or unusually small. It represents a common outcome of galaxy formation in this part of the universe. Its size reflects the typical balance between visible matter, dark matter, and time. In this sense, learning about Andromeda's extent is also learning about spiral galaxies more generally. As this comparison settles, the idea of size becomes less competitive and more contextual. Andromeda is not defined by being larger or smaller than the Milky Way, but by being part of the same class of systems, evolving together within a shared gravitational environment. From here, the exploration can move outward again, toward the regions where the boundaries between the two galaxies begin to soften and overlap. As the outer regions of Andromeda are considered alongside those of the Milky Way, the idea of separate self-contained galaxies begins to soften. On the larger scales, two systems do not exist in isolation. Their extended halos, composed largely of dark matter and thinly spread gas, reach far into the space between them. At these distances, the notion of a clear dividing line becomes less meaningful. Instead, there is a gradual overlap, a region where influence is shared rather than owned. In this overlapping zone, gravity works quietly and slowly. Objects there do not clearly belong to one galaxy or the other. Their motions reflect a balance between competing pulls, shaped by the combined mass of both systems and the broader structure of the local group. Over long timescales, this balance can shift. Material may drift inward toward one galaxy, or remain suspended in a loosely bound state, responding to subtle changes in the surrounding gravitational field. This overlap does not imply confusion or instability. It is a natural outcome of large, extended systems existing in proximity. Because Andromeda and the Milky Way are both massive and diffuse, their outer regions blend long before their bright disks ever approach one another. In these regions, size is no longer about a galaxy's internal structure, but about how far its influence can be felt in the presence of another comparable system. From an observational perspective, this makes measurement more complex. When astronomers study distant stars or gas clouds in the space between the two galaxies, it can be difficult to determine which system they are bound to, or whether they are bound at all. Their velocities may be low, their paths irregular, and their origins uncertain. Rather than forcing a classification, scientists often describe such regions statistically, acknowledging that membership can be ambiguous. This ambiguity is not a flaw in understanding, it is a reflection of reality at large scales. Galaxies are not rigid objects with fixed borders. They are extended gravitational structures embedded in a continuous cosmic environment. Where two such structures approach each other, their boundaries naturally become zones of interaction, rather than lines of separation. Allowing this idea to settle changes how Andromeda's size is perceived. The galaxy is no longer imagined as filling a discrete volume of space, surrounded by emptiness. Instead, it is part of a larger pattern. one in which size is relational and context-dependent. Andromeda's extent is shaped not only by its own mass, but by the presence of its nearest neighbour and the shared history of the local group. From here, attention can begin to shift gently toward time. The present overlap between Andromeda and the Milky Way is not static. It reflects a moment in an ongoing process, one that has unfolded over billions of years and will continue to evolve far into the future. When time is introduced into the question of Andromeda's size, the idea becomes even more gradual. The galaxy we observe today is not the same as it was billions of years ago, and it will not remain as it is now. Size, in this sense, is not a fixed attribute, but a slowly changing condition. Andromeda has grown over time, not by expanding uniformly, but by accumulating material through a long sequence of quiet events. Early in its history, Andromeda was smaller and more compact. Gas condensed, stars formed, and gravity organized matter into a rotating structure. As time passed, smaller galaxies wandered close enough to be captured. These mergers did not usually happen as dramatic collisions. More often, they unfolded over long periods, with stars gradually stripped and absorbed. Each event added mass and extended the galaxy's reach, contributing to the growth of its disk, halo, and dark matter envelope. This slow accumulation means that Andromeda's size at any given moment reflects its past. The extended halo and stellar streams seen today are records of earlier stages of growth. They show where material was added and how it was redistributed. From this perspective, size is not just a spatial measure, but a historical one. The farther outward a component lies, the earlier or more gently it was incorporated. Time also affects how boundaries appear. Features that are sharp and distinct shortly after an interaction tend to smooth out as billions of years pass. Stellar streams disperse, gas mixes, and orbits become more randomized. What was once a clear addition becomes part of a diffuse background. As a result, the outer regions of Andromeda grow less structured over time, even as they continue to expand. Looking ahead, Andromeda's size will continue to change. As it approaches the Milky Way, their shared environment will reshape both galaxies. Material in their overlapping halos will be redistributed, and new extended structures will form. These changes will happen slowly, without sudden transitions. From a cosmic perspective, the present size of Andromeda is simply one phase in a long sequence of gradual adjustments. Allowing time into the picture makes it clear that size is not something to be finalized. It is something that unfolds. Andromeda's true extent is best understood as the current expression of processes that have been active for billions of years and will continue long after the present moment. As understanding of Andromeda's size has evolved, so too has awareness of the limits imposed by observation itself. Every measurement depends on instruments, methods, and assumptions, all of which change gradually over time. What is described as the galaxy's extent is always tied to what can be detected, resolved, and interpreted at a given moment. This does not weaken the science. It simply places it within a realistic frame, where knowledge grows by refinement rather than by replacement. Early observations were constrained by sensitivity. Faint stars, diffuse gas, and subtle motions were difficult to detect, so the galaxy appeared smaller and more compact. As telescopes improved, these faint components came into view. Each improvement extended the known boundaries outward, revealing structure where previously there seemed to be emptiness. This pattern continues today. New surveys regularly identify stars and gas at distances that would have been unreachable only a few decades ago. Method also matters. Different techniques emphasize different components. Optical surveys highlight stars. Radio observations trace gas. Kinematic studies reveal mass through motion. Each method draws a slightly different outline around Andromeda, and none of these outlines is wrong. They are complementary views of the same system, each limited by what it is designed to measure. When these views are combined, the galaxy's size appears larger and more layered than any single method would suggest. There is also the quiet influence of definition. Deciding where one component fades into another involves thresholds, probabilities, and conventions. Astronomers choose these carefully, but they remain choices. A star counted as part of Andromeda's halo in one study may be considered part of the local group background in another, depending on criteria. These differences do not indicate disagreement so much as they reflect the continuous nature of the system being studied. What remains stable through all of this is the pattern of gradual extension. No matter how methods change, Andromeda's structure consistently shows a bright core surrounded by progressively fainter, more diffuse layers. Each layer merges smoothly into the next. As observational limits are pushed outward, this pattern repeats rather than breaks. The galaxy grows in description, but it does not suddenly acquire new edges. Recognizing observational limits brings a quiet balance to the idea of size. It reminds us that Andromeda's true extent is not hidden behind a single missing measurement. Instead, it is approached asymptotically, becoming clearer as techniques improve, but never collapsing into a final, absolute boundary. The galaxy remains open-ended, not because it is poorly understood, but because it is genuinely diffuse. As this awareness settles, attention can begin to move beyond measurement itself, toward the broader patterns that Andromeda's size reveals about galaxies as a class. The details matter, but they also point outward, connecting one system to many others across the universe. When the many layers of Andromeda are held together in mind, a simple pattern begins to emerge. The galaxy does not consist of separate pieces stacked one outside the other. Instead, it forms a continuous structure, where each component gradually gives way to the next. The bright stellar disk fades into a thinner population of stars. That population blends into a diffuse halo. The halo sits within an even larger distribution of gas and dark matter. At no point is there a clear moment of transition. The structure softens rather than ends. This continuity is one of the most important aspects of Andromeda's true size. It shows that the galaxy cannot be reduced to a single outline without losing something essential. Every attempt to draw a boundary captures one aspect of the system while overlooking another. What remains consistent across all approaches is the gradual nature of change. Density decreases, motion disperses, and influence weakens slowly with distance. In this sense, Andromeda's size is best understood as a gradient. Near the centre, stars are dense, motion is fast, and structure is clear. Farther out, stars thin, orbits become less ordered, and light grows faint. Still farther out, matter is present primarily through its gravitational effect, shaping motion without revealing itself directly. Each region is connected to the next through smooth transitions rather than abrupt shifts. This gradient reflects the way galaxies form and evolve. Material does not arrive all at once, and it does not settle into fixed compartments. Instead, gravity draws matter inward over time, while interaction spreads some of it outward. The result is a system with no sharp divisions, only varying degrees of association. Andromeda's size, viewed through this lens, is not a measurement to be finalized, but a description of how far this association extends. Holding this idea allows the question of size to feel calm rather than unresolved. There is no missing edge waiting to be discovered, no final layer that will suddenly complete the picture. What exists instead is a coherent structure that becomes quieter with distance, until it merges with its surroundings. The absence of a boundary is not a gap in understanding, it is a faithful reflection of the galaxy itself. As this sense of continuity settles, the exploration naturally widens. Andromeda's gradual structure is not unique. It reflects broader patterns seen throughout the universe, where galaxies blend into groups, groups into clusters, and clusters into even larger arrangements. From here, the focus can gently expand beyond Andromeda alone, placing its size within a wider cosmic context. When Andromeda is placed within the wider setting of the local group, its size takes on a different kind of clarity. The galaxy is no longer considered only in isolation, but as part of a small community of galaxies bound together by gravity. The local group contains dozens of members, most of them much smaller than Andromeda and the Milky Way. Their motions, distributions, and histories are shaped largely by the presence of these two dominant systems. In this context, Andromeda's size can be thought of not just as an internal structure, but as a role it plays within a larger pattern. Its mass organizes the movement of nearby dwarf galaxies, guiding their orbits and influencing how gas and stars are distributed throughout the group. The farther one moves from Andromeda's center, the more this influence blends with that of the Milky Way and the collective gravity of the group as a whole. Size becomes a matter of participation in shared motion, rather than exclusive control. The local group itself has no sharp boundary. Like Andromeda, it fades gradually into the surrounding universe. Galaxies near its edges move more slowly relative to one another, and the pull of larger-scale cosmic structures begins to matter more. Andromeda's position within this group is therefore both central and contextual. Its size is large enough to dominate locally, yet limited by the presence of other massive systems nearby. Viewing Andromeda this way reinforces the idea that size is relational. A galaxy's extent is meaningful only in relation to its surroundings. Within the local group, Andromeda is one of the primary anchors of motion. Beyond it, the influence of clusters and the broader cosmic web becomes more important. The transition is smooth, guided by gravity and time rather than by boundaries. Allowing this broader pattern to settle softens the focus further. Andromeda's true size is not just how far its stars or dark matter extend, but how it fits into a nested structure of cosmic organization. From here, the exploration can gently turn toward the future, where time and motion continue shaping these relationships. When attention turns toward the future, the size of Andromeda can be thought of as something that will continue to change, not through sudden expansion, but through steady motion and long-term interaction. The galaxy is moving toward the Milky Way at a measured pace, drawn by their mutual gravity. This movement does not imply urgency or collision in the immediate sense. It unfolds over billions of years, on timescales that make individual moments feel almost still. As Andromeda approaches, its outer regions will be the first to interact more strongly with those of the Milky Way. The overlapping halos will become more mixed, and the shared gravitational environment will gradually reshape the motion of stars, gas, and dark matter. In this phase, the idea of Andromeda's size becomes even more diffuse. Its outer extent will no longer be defined by how far its influence reaches alone, but by how that influence combines with that of another large system. Over time, material that is now loosely bound may be redistributed. Some stars may drift outward into broader orbits within the combined system. Others may move inward, contributing to new structures that have not yet formed. Gas may be compressed or stirred, changing its distribution without clear boundaries. These processes do not add edges or remove them. They continue the pattern of gradual transition that has always defined galactic size. Even far into the future, when Andromeda and the Milky Way are no longer distinct in the way they are today, the concept of size will remain layered. There will still be dense regions and diffuse ones, bright concentrations and faint outskirts. The system that emerges will have its own extended structure, fading slowly into the surrounding universe, much as Andromeda does now. Thinking this way allows size to be seen as a temporary description rather than a permanent label. Andromeda's current extent reflects a moment in an ongoing sequence. It is neither final nor incomplete. It is simply the present expression of motion, mass, and time working together. As the exploration of Andromeda's size draws closer to rest, it can be helpful to return gently to the perspective from which the question first arose. From a human point of view, size is often something we try to contain mentally, to make comparable and manageable. We look for numbers, boundaries, and labels that help us situate ourselves. With Andromeda, this instinct meets a structure that resists being neatly held. The galaxy is large in every sense we can measure, yet it remains diffuse, layered, and open-ended. This does not place Andromeda beyond understanding. Instead, it reveals the limits of how understanding is usually framed. When size is treated as a single measurement, something essential is lost. When it is treated as a pattern of gradual change, it becomes easier to hold. The galaxy's extent is not an object to be grasped, but a condition to be observed. Its stars, gas, and dark matter form a system that thins quietly into space, connected more by influence than by form. From this angle, the question of true size no longer asks for a final answer. It asks for attentiveness. How far does light reach? How far does motion remain organized? How far does gravity quietly guide matter? Each of these questions receives a calm, partial answer, and together they form a complete picture without a single edge. For a moment, it is enough to recognize that Andromeda's scale is not meant to overwhelm or diminish. It simply exists, unfolding over distances and times that are steady and impersonal. The galaxy does not announce its size. It expresses it through continuity. With everything now laid gently in place, the Andromeda Galaxy can be held as a system without borders, defined by slow transitions rather than limits. Its true size is not a number written at the end of a measurement, but a range of presence, extending from bright stars to faint motion, from visible structure to quiet influence. Nothing needs to be concluded from this. Nothing needs to be taken away. The galaxy continues as it always has, rotating, drifting, interacting, changing so slowly that stillness becomes the dominant impression. Its size is not fixed, yet it is stable. Not because it ends somewhere, but because it fades naturally into what surrounds it. Everything flows. Sleep in that motion,